In this video, we're going to consider the term activation energy, which affects the rates of a chemical reaction. And the activation energy is the minimum energy required for the bonds to be broken. And in order for bonds to be broken, there has to be a collision. So we're going to be talking about compounds in the gas phase. And so the stability of the reactants and the temperature does affect the activation energy. We're going to draw a diagram depicting the activation energy, and it looks like a hill, or it's an energy barrier that the reactants have to overcome in order to form products. So I'm going to slide this up and actually draw an energy diagram, or we might call it an energy profile, where energy increases going up the y-axis, and this is just the course of the reaction across the bottom. So if we start with reactants, and again, all of our reactants are on the left, products are on the right. So if we start with reactants, the energy goes uphill, and then we'll end up going back down the hill. But this difference right here, from the internal energy of the reactants to the top of this hill, is what we refer to as the activation energy. So reactants don't just go straight to products. There's this energy barrier that must be overcome. So in an example of N2 and O2 reacting to make NO, nitrogen has a triple bond, so that's a very hard bond to break, and oxygen has a double bond. So in order for this reaction to occur, these bonds have to be broken. So to break bonds requires this energy. So that's pretty much what we can think about as the activation energy. There's a few factors that also occur. The orientation with which these two collide with each other affects it. Kind of like two cars hitting head on, or two cars barely grazing each other in a fender bender. So the orientation also plays a role. We're going to look at these energy diagrams and see some one-step or even two-step or three-step reactions. So this overall energy, this difference right here between the reactants and the products, is really the, we could refer to that as an exothermic reaction, where the enthalpy, the overall reaction, goes downhill in energy. So this would be an example of an exothermic reaction, where the products are lower in energy than the reactants. So this is the most common form that we would see, an exothermic reaction. If we look at an endothermic reaction, for example, this one, if we had N2 and O2 making two NOs, here the reactants are lower in energy than the products. So this reaction is probably not likely to take place, which makes sense if we think about this being our atmosphere. Nitrogen and oxygen don't combine and make NO. But again, we'll look at the activation energy. It's the energy difference from the barrier, or from the reactants to the top of this barrier. So this would also be an activation energy, and the difference right here between products and reactants would be the delta E, which we often refer to as delta H. So the heat of the reaction, if there's no pressure change, then these two are generally the same. So this would be an endothermic picture. Oops, I think I spelled that wrong. So this is really not common. A reaction is generally not going to proceed if we have to add energy in order to do that. This is also a one-step reaction because we see one barrier or one hill that we have to overcome. In the next piece of paper, I'm going to show a two-step reaction, and we'll see that by, we'll compare that with a one-step reaction. So a two-step reaction, we can't really tell if a reaction occurs in multiple steps, but we can sort of theorize that it does. But a two-step reaction would be, for example, if we have A plus B forming products, but we may know that A plus B makes an intermediate, some product X, and then that product X, the intermediate product, turns into the actual final products. Okay, so this would be the overall reaction, and this we might hypothesize would be step 1, and this would be step 2, and the net result, because X occurs on both sides of the equation, the net result is still A and B forming products. So a two-step reaction, the energy diagram is going to look different. And so let's just say that we know that this second step is the slow step. So we can measure a rate, we can actually detect this intermediate, and we know that the second step is the slow step. So the way the energy diagram is going to look for that is, I'm going to put that here, hopefully you can see that. Energy increases going in this direction, and if we start with A plus B right here, it might be pretty easy to get to the intermediate X. And then this step, the slow step, is going to have the largest energy barrier. So we have an activation energy here, that's an E sub A for the first step, and then the second step from X, the intermediate, getting up over this energy barrier, that's another E sub A. So this is a large hill or a large energy barrier. So we can see if it requires a lot of energy for this second step to occur, then this is really going to end up being the rate determining step. Because the slow step is really what's going to cause the entire reaction to be slow. And we're going to look, when that's the case, if we have a reaction that we know occurs in one step, or we know that it occurs in two steps, or even three steps, we can see the energy diagram. We'll see two barriers for a two-step reaction. Again, X is an intermediate. And then the top of here, we'd have very short-lived species here. But this would stick around long enough for us to detect somehow. So if we know that we have a reaction that occurs in multiple steps, we can look at what's called the molecularity of a reaction. And this has to do with elementary steps. So if we have a one-step reaction, so if the reaction occurs in one step, then we can use the balanced equation to write the rate law. So in the balanced equation, it doesn't really determine the rate law, but the balanced equation really gives us the rate law. So up to this point, we have just talked about looking at data and determining the rate law. So for an elementary step, I'm going to look at this here, and then we'll compare that to the rate law. So let's say, for example, we have a reaction in which compound A goes directly to products, and we only have 1 mole of A, so we could write the rate law. Oops. Rate equals Ka to the first power, because we only have 1 mole of A. We could have an elementary step where we have 2 moles of A turning into product. So if this occurs in one step, then the rate law would be Ka squared. Or this is unusual, but if we have 3 moles of A, and 3 moles of A creates products in one step, then we would have a tertiary rate law with a 3 here. So this is not normal. We could also have 2 reactants, A plus B, making products in one step. So that's really the thing here. An elementary step means A plus B slam into each other and make products in one step. In this case, the rate law would be Ka to the first power, B to the first power, because the number of moles here is understood to be 1. Generally, we find this first. Find the rate law, and then we draw conclusions about how many steps the reaction might occur in. So we'll look at an example in just a minute. If we know that we have a 2-step reaction, and we know the balanced equation for the slow step, then we can write the rate law from just the slow step, because the slow step is what's going to determine the overall rate.